Good morning, champs. Imagine a fluid flowing over a flat plate. Far away from the surface, the fluid moves with a constant velocity, which we call u infinity. But right at the wall, something surprising happens. The fluid velocity is exactly zero. So, somewhere between the wall and the free stream, the velocity must change. And it turns out this change does not happen everywhere. It happens inside a very thin region near the wall. This region is called the boundary layer. Let's start from the governing equations. For incompressible flow, continuity tells us that the divergence of the velocity field is zero. And the Navier-Stokes equations describe the balance between inertia, pressure, and viscous forces. We now consider a steady two-dimensional flow over a flat plate. So the velocity field has two components, a horizontal velocity u of x and y, and a vertical velocity v of x and y. The key boundary conditions are the following. At the wall, where y equals 0, we have u equals 0 and v equals 0. This is the no-slip condition. Far away from the wall, u approaches u infinity, and v is approximately 0. So we have a strong velocity difference between the wall and the free stream. Now here is the key observation. The fluid does not adjust over the entire domain. Instead, the change in velocity happens only in a thin region near the wall. We define this region as the boundary layer. Its thickness is called delta of x. At y equals delta, the velocity is approximately 99% of u infinity. Now the question is, why does this boundary layer exist? The answer is viscosity. Because of viscosity, momentum is transferred from the fast-moving fluid outside to the slower fluid near the wall. This creates a strong velocity gradient close to the surface. In the Navier-Stokes equations, viscosity appears as second derivatives of velocity. Near the wall, the velocity changes rapidly in the vertical direction, so these derivatives become large. This means viscous effects are important only in a thin region near the wall. Now we introduce the key simplification. Inside the boundary layer, the velocity changes much more strongly in the vertical direction than in the horizontal direction. So the derivative of u with respect to y is much larger than the derivative with respect to x. And even more importantly, the second derivative with respect to y is much larger than the second derivative with respect to x. This is the central scaling idea. Because of that, the x momentum equation simplifies. We neglect the viscous diffusion in the x direction and keep only the diffusion in the y direction. So the equation becomes density times u times du by dx plus v times du by dy equals minus dp by dx plus dynamic viscosity times d squared u by dy squared. This is the boundary layer equation. There is one more important simplification. Across the thin boundary layer, the pressure does not change significantly in the vertical direction. So dP by dy is approximately 0. That means the pressure inside the boundary layer is imposed by the outer flow. So what is the physical meaning of the boundary layer? It is the region where viscous effects are important, where velocity gradients are large, and where shear stress is generated. The wall shear stress is given by dynamic viscosity times the derivative of velocity at the wall. So the thinner the boundary layer, the larger the velocity gradient, and the larger the shear stress. Finally, the boundary layer grows as we move downstream. Near the leading edge, it is very thin. Farther along the plate, it becomes thicker. So even though the boundary layer is thin, it controls friction, drag, and many important physical effects. In the next video, we will assume a simple velocity profile inside the boundary layer and use it to calculate the wall shear stress.